Hi, good morning, everyone. So, I'm Hiroaki Kanno in Nagoya. I'm supposed to be the chair of this morning session. So, since it's on time, let's start the morning session, the second day of the workshop. The first speaker is Professor Kondian. He will tell us a morphism between two QFTs. So, please start.
Thank you very much. So first, I want to thank the organizer of the conference for to invite me to give the talk in this conference. So yeah, I'm very grateful to have this opportunity to say something that I rarely had opportunity to say this to talk about the subject. It's the subject is from the reference I least on the paper on the first page. You can see that it's pretty late, pretty early, maybe already 8 years ago. However, I feel that this subject has become and more relevant in the recent research in both mathematics and the physics. So I feel that maybe it's good time to review this subject, especially in the recent year. The topological symmetries or categorical symmetries in the study of quantum field theory become such a hot topic, and you can see that many ideas of the topological symmetry actually already embedded in this work in 80 years ago. Perhaps what we want to emphasize is that this notion, which is expressed in the title, a morphism between two quantum field theory, I believe that it's very fundamental notion, which might be useful in the later research in many people's research, hopefully. Okay, so so a morphism between two mathematical objects of the same type, such as group algebra representations or categories, important thing that the map is the morphism is required to preserving the defining structure of the mathematical object. Okay, this is very important. Morphism usually preserving the defining structure of the mathematical object. And it is arguably the most important notion in mathematics. Well, if you take a categorical point of view, the most important notion is the morphism. Well, ironically, such a notion for physics system has never been introduced in physics. Okay, so that's something strange. Physics almost don't consider this kind of thing. Okay. So in about 2015, we introduced the notion of morphism. Okay, importantly, this morphism is preserving the structures. Okay, between two topological orders. Later on, we realized it can be not well. It can be automatically generalized to other quantum physics or quantum field theories in general. So in this talk, I will review the notion and some of the applications in the study of topological order and quantum liquids. Okay. All right, the obvious question is how to define a morphism between the two quantum field theories. Actually, it's not that entirely unknown. Okay, there is a well-known answer. Okay, a usual definition of morphism between two quantum field theory is a domain walk between two quantum field theory. Okay, if you condense matter physicists, you can automatically change quantum field theory to any quantum many-body system. Okay. All right. Well, if you were maybe quantum information scientist or quantum working on quantum computing, you may be replace it by not necessary many-body quantum physics. Maybe it could be yes. Questions?
Sorry. What do you mean by T's? I mean,
what do I mean?
Is it defined by some Hamiltonian?
I mean, any many-body quantum system, yes, it can be Hamiltonian. But if you are familiar with quantum field theory people usually don't use Hamiltonian, they will use Lagrangian.
So what kind of ingredient are you assuming on about QFTs? Some partition function, correlation function, or?
Well, partition function, all of these things are ingredients of quantum field theory. But I assume that you can start with any your favorite definition of quantum field theory. For example, you can start with the conformal field theory, which have no Lagrangian description. that still
Yes.
works.
So
Yeah.
what is the main assumption on your QFTs?
No, there's no assumption, basically.
Oh, okay. Okay, so let's
Uh,
proceed.
Okay, yeah, basically at this stage, there is no assumption. Okay, you can see at some point I will tell you what assumption is needed in order for certain things to make sense. But at this stage, you don't need any assumption. For example, okay, well, the morphism is just a relation between two quantum field theory. A simple way to define the relation, just simply define it as the domain wall. A domain wall between two quantum field theory. Okay, so what is domain wall? So I draw a picture here. You have two quantum field theory, you draw the domain wall. Okay, the domain will provide a physical realization of the mathematical notion of quantum of bimodules, because the domain wall automatically equipped. Okay, it naturally equipped with two-side action of the operator from two QFTs. Okay, so I draw this picture. So you can have some observable or operators in the quantum field theory one. These operator acts on the domain wall from left. You can also have operator from QFT2. They will act on the domain wall from right. Okay, so they automatically support action from two sides. Okay, but now for this, you don't need any assumption. Okay, but if you want to compose morphism, you want associativity of the morphism, then you need a certain assumption. Okay, but well, at this stage, we don't need to talk about that. Okay, just the morphism can be defined as a domain wall. I think here you don't need any assumption. Okay, however, this definition of morphism as a bimodule is less fundamental. Why is that? Because it does not preserve the algebra structure of quantum field theory. Okay, as a consequence, such a definition of morphism as bimodules assume we will have a nice defined category using this morphism. Then you can see that using this definition of morphism, it can only distinguish quantum field theory up to Morita equivalence. Okay, simply because the definition of morphism does not preserve the algebra structure of quantum field theory. Okay, but this is widely used in physics. Okay. So obviously, the natural question is that in mathematics, there is a more fundamental natural notion of morphism between two algebra objects, right? The map, the important thing is that the map is preserve algebra structure. For example, group homomorphism, okay? Well, it have to preserve the identity and preserve the multiplication. Okay, I ignore the identity, just write the multiplication. Similarly, you have algebra homomorphisms, okay? It also have to preserve the multiplication. Similarly, you can have a monoidal functor between two monoidal categories. Okay, again, the functor is preserved multiplication. So whatever the morphism you choose, you have to preserve the defining structure of the mathematical objects. Okay, these are examples of morphisms, homomorphisms, okay, between two algebra objects. So the natural question is, what is the physical realization of a notion of algebra homomorphism instead of bimodule? Okay, or equivalently, you can ask more directly, how to map a quantum antibody system or a quantum field theory to another, such that the algebra structure of the operator or observables are preserved by this map. Okay, that's a very obvious and natural question to ask. Interestingly, I don't know much about the reference. I don't know any physicists asked this question before. Anyway, okay. So before we introduce the notion, we need some preparation. The terminology will be used in the following few slides. Okay, I will use topological orders, which means some gapped quantum phases at the zero temperature. Okay, it's a gap to physical many-body systems. Or if you are more mathematically oriented, you can just treat topological order as topological field theory. Okay. However, in the end, this notion will be generalized and will be replaced by a much more general notion called quantum liquid. And the quantum liquid can be gapped, can be gapless. So that means we're going to introduce some kind of notion which is not necessarily topological, but including the case which is topological. But this notion is a little bit hard to define. Okay. It's a little hard to define. So for convenience, we restrict our discussion to the familiar notion of topological order at first. Okay, so let me emphasize what is topological order one more time. If you're a condensed matter physicist, you can view topological order as quantum phase, gapped quantum phase at the zero temperature, and satisfy certain finite properties. Okay, if you're more mathematical oriented, you can just treat it as topological field theory. Okay. All right. Okay, so let me first introduce the definition. A topological order is called anomaly free if it can be realized by a lattice model in the same dimension. It is called anomalous if otherwise. Okay. For example, a gapped boundary of a non-trivial topological order are example of anomalous topological order. Okay, because it is a gapped boundary. Very often, this kind of gapped boundary can only be realized as a boundary of one-dimensional higher lattice model. That lattice model realizes a higher dimensional phase. So this one we start with is only a boundary of that. You cannot live without that boundary. Okay, that boundary very often is also called the gravitational anomaly. So that's why it's called anomalous. Okay, a gapped boundary of a trivial topological order or a trivial phase is viewed as anomaly free topological order. Okay, so that's just some kind of remark, I guess. Yes.
Again, what is a
Yes.
lattice model? Usually, I understand lattice model is defined by some Hamiltonian, but
yeah,
you said that you didn't assume, you don't assume any Hamiltonian for your QFT.
Oh, at the very beginning, oh, no, yeah, let me clarify this. Yeah, you asked a very good question. At the very beginning, I talked about the quantum field theory. That's very general. Now I restrict the subject a little bit. I restrict to topological field theory for now.
And so by a lattice model, you assume some Hamiltonian, is it right?
Yeah.
Okay. So
I assume that it's kind of a topological field theory which can be realized by lattice models. So this is some kind of a field theory with a UV completion or something. Yeah.
Okay, thank you.
Yeah, that's a very legitimate question. Yes, thank you for asking. All right, so all right, so once we have these notions, then we will say, so from now on, when I talk about topological orders, it always means potentially anomalous. So it could be anomalous, okay? In general, it is anomalous. So a topological order AN, and subscript n represent the dimension, okay, has a unique anomaly-free topological order as its block, one-dimensional higher. You see, this n is a space-time dimension, and this one is one-dimensional higher. So what I put in here, you can view it as a hypothesis or as a principle. In this paper, we provide a physical argument of why it is true. But depends on how rigorous you prefer. If you're a mathematical physicist, like maybe like Professor Ogata, I believe that she will definitely treat it as a hypothesis instead of a principle. Okay, our argument is not that physically rigorous. Yeah, but still. So what we argue is that for anomalous n plus nd topological order, there is a unique anomaly-free topological order can be viewed as its block. Because it is unique, we can denote it. We can introduce a notation for it. Okay. Remember, the subscript always represent the dimension. Okay. Let me give an argument. Let me give some not argument. Let's give you some understanding of why this is true. Okay. So an anomalous topological order must be realizable. Okay. Remember, this cannot be realized in the same dimension cannot be realized by a lattice model in the same dimension, but it must be realizable as a defect of a higher but still finite dimensional lattice model, right? Well, if not finite, well, you can safely to say, okay, otherwise it is safe to say such topological order does not exist, okay? All right, if it is realized as a higher codimensional, okay, it's some kind of a higher codimensional defect in a higher dimensional lattice model, such as this picture was drawn in here, okay? What you can do is that you drag this point, okay, to the left, and the whole thing looks like a cigar, and you squeeze the cigar to one-dimensional, only one-dimensional higher. You produce so the last step is a dimensional reduction process. Okay, so what we're saying is that, okay, this AN can be realized as a higher codimensional defect in the higher lattice model, yes, but this realization in general is not unique. Okay, you can have many examples to show you that this is not unique. You can find many ways to realize these things. But if you do the dimension reduction as drawn in these pictures, you get one-dimensional higher anomaly-free thing. What we claim is that this anomaly-free thing is unique. Another remark I want to make is that this ND topological order, which is viewed as the boundary of this whole thing, should be viewed as a boundary phase in the sense that when AN is defined, it's defined in the neighborhood of the boundary. It's not just on the boundary. It's defined in the neighborhood of the boundary. Okay, so in that sense, it determines the block. Okay, for topological phases, the size of neighborhood is not important because if you assume infinite gap of the block in that limit, there isn't really no length scale, preferred length scale. So the size of the neighborhood is not important. That's why it determines the block. That's the vague argument. Okay, well, I won't go further on this. I ask you to believe me on that. We can come back to this after the talk. All right, so I will give you some examples. So if dn minus 1 is a domain wall between an and bn, okay, as drawn in this picture, okay? Now what you can do is you can fold the system to get a double layer system with an and bn bar. Bn bar just means the time reversal of b because the orientation of the system is flipped. So it's corresponding to flip the time, okay? So in this case, dn become a boundary of the double layer system. As a consequence, okay, the bulk of dn is a double layer as well. Okay, that's very easy to see. I will give you a special case when a, b, d are the same. When a, b, d are the same, so this an minus 1 is nothing but you just fold a single system artificially. You break it into two, well, not break it, you fold it and you get a double layer system, and you artificially you got the boundary, and that boundary I would denote as an minus 1. Okay, so an minus 1 is really denote an restrict to the trivial domain wall of codimension 1. Okay, of course, in this case, D, A, B are the same. So the center of an minus 1 is double A. Okay. All right, that's one example of the block. All right. Okay, let's continue. Let me give another example, almost trivial one. So one denotes trivial topological order. Okay, what is block? Well, it's already trivial, so its block is also trivial. Okay. Moreover, if a topological order is anomaly free, if and only if its block is trivial. If the block is trivial, that's already simply tell you that okay, you can sort of realize the phase of the same dimension. Okay. Similarly, you can also have the bulk of bulk is trivial. Okay, you take one bulk once, take a bulk twice, you got a trivial one. Why is that? You look at this picture. Okay, A have a bulk which is already anomaly free. You take bulk of that, it's trivial, it's empty. Okay, it's completely empty. Okay, I want to make a remark of this. This looks pretty naive, right? But the statement of the bulk of bulk is trivial is somewhat due to that the boundary of boundary is empty. Okay, which inspired homology theory. So therefore, we expect that the bulk of bulk is trivial should lead us to some non-trivial cohomology theory, which is still completely unknown. Okay, that's just one remark. All right, now we enter the most important. Yes.
And I don't understand second item. Second item, an is anomaly free.
Yeah.
I mean, you are, according to your definition, anomaly free is defined by some lattice model.
Yeah.
But
right.
I don't.
When the lattice model is realized in the same dimension, so an is normally free, so it can be realized by a lattice model in dimension n, right?
Yeah.
So that means it's n plus 1 bulk is trivial. Imagine that you already realize this, so you have a two-dimensional topological order which is normally free. You realize this model in 2 dimensions. Then its 3-dimensional bulk is completely empty, right?
But how does lattice model enter in your argument?
and okay, look,
the condition.
say you have a two-dimensional material. Okay, you use a lattice model, realize it. Then it's one-dimensional higher bulk is completely empty. It's a three-dimensional bulk.
Yeah, and I understand, but why lattice do you use lattice model? I mean, any model realization seems to be possible in your discussion, in your argument.
Oh, I see.
That in particular.
I'm not sure. I would say what I assume is that everything physically can be realized in the same dimension can all have lattice model realization. That's what I secretly assumed.
I see.
Any physically anomaly-free system without any including no framing anomaly or other anomaly can all be realized by lattice in physically. Any physically realizable, I assume it can be realized by lattice model.
For example, if we can realize the theory in terms of some Hamiltonian, not necessarily lattice model.
You were saying, well, I don't know what's the difference between lattice model and Hamiltonian. For me, lattice model is always equipped to Hamiltonian.
I see. Yeah. But so in general, if the system is realized as some Hamiltonian system, not necessarily a model, then does your argument work?
Well, I assume it's gapped.
I see. Gapped Hamiltonian, you see.
Yeah, gapped Hamiltonian. And you consider the phase. I also essentially assumed infinitely large gap. Because I consider zero temperature. Yeah. Only zero temperature.
In terms of the lattice model, gapped Hamiltonian. If we realize some gapped Hamiltonian. Okay, see.
Gapped model. Yes. Yeah. This thing is tricky. But if you, for example, if you consider gapless cases, there are a lot of cases which you don't have a lattice model realization. That I don't know how to discuss them, but it's excluded in this case for now. Okay, because I only talk about topological order. If you consider like a 1+1D conformal field theory, which is gapless, a lot of things here still works. But I don't know what kind of lattice model realize them. But the argument here still works. We got to talk about those things later, yeah. But there are quantum field theory that might not have a lattice model realization. That's also possible to feed in our argument. Okay. All right. Can I continue? Yeah. All right. Okay. I think I'm a little short of time, but let me. Okay. So the most important concept of this talk is to introduce the morphism between two topological orders, A and B. Okay. F between A and B, how are we going to define it? It turned out we're going to define it as a gapped domain wall, Fn, okay, between the bulk of A and the bulk of B. Why is it meaningful? Okay, what does this mean? Okay, because it is topological order. Okay, because it is topological order, everything is gapped. Okay, then this fusion is well defined. Okay, but if you condense matter, you don't like a fusion, you can do cross graining. Okay. Okay, so what is F is the domain wall, okay, and this is drawn as a line here, and A1 is a one-dimensional lower. It's just a boundary. Now you can fuse them using this. When you fuse them, assume the fusion is well defined, but it is well defined for topological field theory. Okay, then you can identify this with B. Okay, when you identify this with B, clearly this is legitimate, right? This is the bulk of B. Right, this is just bulk of B. So F is a domain wall between bulk of A and the bulk of B. Okay, that's how I define the morphism. All right, now the composition of two morphism can be easily defined. Okay, if you have a morphism A from A to B, okay, that will be F will be a domain wall between the bulk of A and the bulk of B. Okay, now you have a morphism from B to C. That will be a domain wall between bulk of B and bulk of C. Okay. As a consequence, how to define the composition? The composition is nothing but by fusing this two, fusing Gn with Fn along the bulk of B, you got, by doing this fusion, you got the domain wall between bulk of C and bulk of A. That's exactly our definition of a morphism from A to C. That's how you define a composition. Okay. Now I want to explain why this definition give you a notion of a morphism. The idea is this. Okay, you want a map which preserve the algebra structure of the quantum field theory. Okay, so in this case, if using this simple way to draw this, you won't see the algebra structure. In order to illustrate some kind of algebra structure in the quantum field theory, I draw a one-dimensional higher. Okay, one-dimensional higher picture. You can see it better. For example, in this A, now I draw it as a one-dimensional higher. In this case, you can have some local fields or local observables or local operators or topological defect. It depends on what context you like to view these things. Doesn't matter. Okay, let's just view these operators as a A1 and A2 and AK. Okay, now you can fuse these operators or multiply them along the line, right? You hope that the map you introduce will preserve this algebra structure. Yes, indeed. Look at this picture. This F is nothing but a domain wall between bulk of A and the bulk of B, right? Okay, you see the idea of how we come up with this is that if you do F in this way, it won't monitor the algebra structure of A directly. It only massages it from outside. You see, if you want to keep the algebra structure of the system, you cannot cut through the system. If you cut through the system, you break the algebra structure inside the system. Only thing you can, if you want to preserve the algebra structure of the system, only thing you can do is you do some massage from outside. But what is the outside for anomalous topological order? Outside is nothing but the bulk of the topological order. So the only thing you can do is inside the bulk of topological order. Okay, so that's why it becomes a domain wall between two bulks. Okay, and you can see that, you can see from the picture, you can already see that this preserved the algebra structure. Okay, this fusion is similar to the tensor product in the Euro mathematics. Okay, just relative tensor product. Indeed, now I want to give you some mathematical result to justify this statement. It turned out that this definition of morphism coincided with the mathematical notion of a monoidal functor between two fusion n categories. In particular, you have for example, you have a monoidal functor between two fusion categories. Let's say fusion one category. Okay, in this case, it's just represent the fusion one category will represent a mathematical description of 1D topological order. Okay, so given such a monoidal functor, you can build a domain wall in this way, because this monoidal functor automatically equipped B as AB bimodule. Okay, you have a B action from right automatically. You also have a left action from A, a left A action induced by the monoidal functor F. Okay, in this way you can get this functor category. This functor category turns out exactly is the domain wall between these two. Okay, and it can even go backwards. Once you have this, so what's the domain wall? Remember, domain wall is a bimodule. So this turned out to be automatically a bimodule between ZB and ZA. What is ZA and ZB here? ZA and ZB, it turned out to be the dream field center. Okay, this is the dream field center of fusion category B and the dream field center of fusion category A. Okay, you can even go backwards. Okay, that's pretty obvious. These two constructions are inverse to each other. You can prove it. All right, that's give you some idea why this notion is mathematically reasonable. All right. Okay, then we can forget about math side and let's play with the picture. Okay, how to define an identity map? Identity map can be defined as a trivial domain wall in the bulk of A. Okay, you just restrict to the trivial domain wall. Okay, just change the dimension, and you can see fusing this two, you got A because remember, A is the boundary field. You know, you just choose a trivial domain wall in the bulk. It won't change the. You can choose this wall at anywhere you want it. It's just doing nothing. Okay, so it's just equivalent to say that the boundary face is defined in the neighborhood of the boundary. Okay, that's identity map. There's another obvious map is that from any trivial topological order, there is a canonical morphism from the trivial topological order to a non-trivial topological order defined by this. Okay, you start with the trivial one. Its bulk is also trivial, and now you need a domain wall between the bulk of the trivial one and the bulk of A. Okay, yeah. Well, what's that thing? That's just A itself. Okay, you fuse this to get A. All right, that's an obvious morphism. All right, I want to intentionally go a little slower. Because the magic will soon happens. Okay, now I want to introduce a slightly non-trivial morphism. Okay, if you the bulk of A, you restrict to the trivial domain wall. That's denoted by N. Okay, ZAN. Okay, so what is how you get it? Now I claim that there is a canonical morphism from ZAN. Stacking. This tensor product represents the stacking. That just means in space you have these two connected by vacuum. There's nothing in the between. This empty thing. Okay, that's a stacking operation. And there is a morphism to AN. How to define that? It's defined by this picture. Okay, notice this blue box. This blue box represents the domain. Okay, represent the domain. Okay, they're just stacking two things, right? And their bulk, what is their bulk? The bulk of A is denoted by this, right? And what is the bulk of ZAN? Well, that's double layered, right? It's double layered. Okay. Now, how to define a morphism? All right, you just pick this this almost like a green. So this M, okay, is defined in this box. It's a domain wall between the bulk of these two. The bulk of these two is a 3-layered. Okay, the bulk of these two, the bulk of this. Okay, sorry. This box is a domain wall between bulk of the domain and the bulk of the codomain. Okay, you can see why it's true. It's very tautological. You just have the same bulk. You just fold it in a few, 3 times. Only 2 times, I guess. Yeah. Then you got this picture. Okay. You can straighten it. Why you fuse in this way? You got A. So that justifies the codomain of the map is AN. Well, that's obvious, right? Because it just straighten out. You just straighten out this zigzag picture. You got a trivial one. It's just A with a bulk. That's all. Okay. This is non-trivial map. All right. That's the only non-trivial thing, I guess. Now I want to make a claim. Okay, I want to make a claim is that this ZAN together with M I just defined, okay, satisfy the universal property of the notion of center. That is, if X is another ND topological order equipped with a morphism, okay, XN a box tensor AN to N, A to A, AN, then there is a unique morphism F prime from Xn to ZAN such that the following diagram is commutative. All right, if you're familiar with the notion of center, the universal property of notion of center, you will see immediately that this is the universal property of the center. That exactly just means that this theorem simply say that the bulk is the center of the boundary. Okay, if you haven't seen it, if you haven't seen this before, it's difficult to see what's going on in a 1 hour talk, I believe. But I want to give you some comments. Okay, what the universal property works? It works for all the notion of center. For example, okay, in this picture, you see this universal property is only defined using notion of morphism. Once you know the notion of morphisms, you define the notion of a center. Okay, for example, if you have all this notion living in the category of a group, okay, let's say A is a group and M is a group homomorphism, and this universal property recover the center of a group. Okay, if A is algebra and M is algebra homomorphisms, then it recover the Euro center of algebra, which can be defined set theoretically. Okay, that's just a sub-algebra which commute with all the element in A. Okay, that's the very famous definition. But this set theoretical definition is not very useful for quantum field theory. So we need a universal property to define it. That's more convenient. Okay, for the advantage of that is you can realize many seemingly very different concept as the same concept, but living in a different category. For example, if you take take A as a fusion category or just a monoidal category, M is a monoidal functor, then it recover the famous Dreamfield center. Okay, if A is a braided fusion category and M is a braided monoidal functor, then it recover the so-called Muger center. Okay, and so on and so forth. There are many, many examples. For I can tell you another example is the center of the open string CFT is the closed CFT. In this case, it's called the full center. But anyway, there are many of such things. If you're familiar with the mirror symmetry, in the word of mirror symmetry, there is a famous generalized link conjecture, which says that the En center of En algebra is an En plus 1 algebra. In that case, you got the same universal properties, except you can replace everything by En algebra. And M will now become a En algebra homomorphism. And in this case, you define an En center. Okay, so they all satisfy the same universal property. That's why they're all called the center. Okay. All right. So what does abstract nonsense theorem really tell you? Actually, it recovers some highly non-trivial previous results. Okay, I have only 5 minutes left. Okay, so for example, in 2 plus 1D non-chiral topological order, we have already recovered the well-known result, which says that for a 3D topological order, it can be described by a modular sensor category. Okay, and its gapped boundaries can be described by a fusion category. Okay, moreover, we have the Dreamfield center of the fusion category associated to the boundary is nothing but the bulk. Okay. Moreover, you can have a different boundary. You can have a different boundary. Okay. And they share the same bulk. They share the same bulk. More result can be stated. Okay. This X is invertible MN bimodules, turn out. Okay. This domain wall between different boundaries. Domain wall between different boundaries are exactly invertible L-N bimodules, which define the Morita equivalence. Okay, this is just a physical realization of the mathematical theorem, which says that two fusion category Morita equivalent if and only if they are shared the same center. Okay, by Adingolf and Nikschik and Ostrich. Okay, so you can see that this theorem is non-trivial. Actually, I can make the theorem even more non-trivial. Is that now I have skip some. Let me just skip some details. Okay, so actually you can generalize the theorem to a more general one. So MMN are fusion N categories, which can be defined, and X and M are bimodule, not necessarily invertible. Okay, here I assume here X is invertible, so there's nothing on it. It's just sort of just between M and N, L and M, that's invertible. But here I assume general bimodule. If you have a general bimodule, it turns out that this one also support a relative bulk. Okay, this relative bulk can be mathematically defined as a relative center. Okay, relative to the respect the action of L and M. Okay, so that's also a center. Okay. What is interesting is that if you do this assignment, if you assign L to its center, and you assign the Dreamfield center is nothing but this, but it's still the bimodule functor category. Now X, you assign this one is some kind of relative center, generalizing this. It turned out it defines a functor. Okay, what does this mean? It means in particular it means this. For each X, you can assign this one. For Y, you can assign this one. Okay, then you can either do the relative tensor product of this. That means fusing this two domain wall along the bulk, along their bulk. Okay, and the result is compatible with. Okay, you first fuse them on the boundary. You fuse this thing on the boundary. Okay, together with Y. Okay, X and Y, you fuse them on the boundary. Then you compute the relative center. They're compatible. This is physically just tell you that that theorem actually tell you that this have to be true, but it turned out to be a mathematical theorem. You can prove it. But of course, the mathematical theorem, to prove a mathematical theorem is much harder. Okay, not only that, we can even I can tell you why the notion of morphism here is useful. Why this thing is so useful? We can prove a very strong theorem. So I want to tell you that a very strong theorem For the time being, maybe I will just skip this slides. I will skip this slide. Just tell you that this formula is very useful. It has been used in many work in our further studies. Okay, have some other physical application. Now I want to tell you the results. That do I have time? Wait, I'm almost approaching the end. So let me explain this. Wait a minute. I still have some. Okay, so I don't think I have time to explain this result. I just want to show you that maybe just let me state the result. When n equal 1, yeah, excuse me?
Minutes, please.
Yeah, I probably don't have time, so let me skip the detail. Let me just state I don't talk about the proof. So when n equal 1, this center functor is actually a monoidal equivalent. So that means that the x determine the relative bulk. Conversely, this bulk also determine x uniquely. This can be proved using the notional morphism almost trivially. Okay, because when you say x have a action of Lm from two sides, you translate it. That's equivalent to say there is a monoidal functor from this to this. Okay, that's the same thing. Okay, but remember that once you have a monoidal functor, you can define it using a domain wall. Monoidal functor. Remember, you have a monoidal functor. You can define it as a domain wall. But look at this picture. You have this map to the domain map to the functor x is the center of x. That means you just fold this together. Or how you get this part? You just fold from this picture. You fold it. You get a double layer system. Okay. Then you get this picture, and you further fold it. You get this one, and this one is simply a functor xx. So there is a physical proof of this statement, make it very obvious. So monoidal functor is nothing but this domain wall. This domain wall is just that. So to say x have a bimodule structure of LM bimodule is equivalent to say there is a domain wall to make it to like this. So these two things are simply equivalent. Okay. So this idea is to just tell you that this is one-to-one corresponding to each other, and this result become a non-trivial because it automatically include the two famous results in mathematics in the field of fusion category, which says that the AB are Morita equivalent if and only their center monoidal equivalent, and moreover, it also includes the following famous result: the Brauer-Picard group of A is automatically is equivalent is isomorphic as a group to the braided automorphism group of the center of A. Okay, for n bigger than 1 is not an equivalence. All right, I'm kind of lost time, so let me just give a remark. All this discussion so far also work for rational CFT, which is gapless phase. So the notion of morphism also work for more general context. We can be generalized, can be gap or gapless. We will call that the mysterious concept called the quantum liquid. If you're a mathematician, if you want a more precise definition, you can treat it simply as a certain fully dualizable quantum field theory. Okay. Without giving much detail, so let me jump to the last, almost the last page. I want to say, okay, so what is the upshot? In the end, we have morphism, we have all these things. In the end, you can even compute the quantum category of quantum liquid. And so that means the category of quantum liquid, that means category of a large amount of quantum field theory can be computed precisely. That's a surprising result. I want to make it mysterious. Let me summarize my talk. The main goal of this talk is to introduce the notion of morphism between quantum field theory and to show that it is useful and powerful. Okay. And similar to the fact that the category theory was once revolutionized algebra geometry by Grothendieck and his schools, we believe that it will also revolutionize the theory of quantum field theory, phase translation, and perhaps quantum gravity as well. So the most important thing is not to borrow categorical language for physical use, but also to use the spirit of category theory to ask new questions and find new truths. To define the notion of morphism between quantum field theory is only an example of many possibilities. Okay, so the last word I want to say is that if the notion of morphism is arguably the most important concept in mathematics, it's only reasonable that the notion of morphism between quantum field theory is an important concept in physics. Thank you very much.
Thank you very much for a nice talk. So, are there any questions, comments? from online participants? No?
So I'm sorry. So I could not follow your talk because this is too mathematical. So could you explain some relationship with some physical phenomena and your topic?
I don't know how it will relate to any physical. Maybe you're asking, does it have any physical applications? More accessible application that yeah. Well, you see, if you categorical thinking is also very alien to many mathematicians who don't use category theory. So I totally agree that if you see this first time, it's so formal, it does not seem to be useful. But I have to say that this is a subject is not we work on it 8 years ago, and we write an isolated paper and leave it without using it. No. This subject has been used in all our paper afterwards, almost every one of them. We use it in many physical applications. It has a lot of deep consequence. So, for example, this is one of the consequences that I think it is the first time you can compute category of quantum field theory. For example, I want to give you for example, is when n equal to 2 or 3. I forgot nd. Nd. Oh, okay. So for nd, that's n is when n is 2. When n is 2, this so-called slice category, very simple category, actually not very simple. It's very rich category. It's actually is exactly the category of rational, all the rational CFT. This statement is already very wild, almost unbelievable. Yeah.
By the way, you use anomaly free. Anomaly is somehow very famous physical phenomena, and this is work by president of SUSTEC.
Yeah.
That do you have some relation with anomaly in the physical sense?
Yes, anomaly in the physical sense. This theory recently have been used in many studies by quantum by high energy physicists to study, especially the 't Hooft anomalies. This also have been used to study gravitational anomalies. 't Hooft anomaly is more natural. It's no, I mean more have been more studied by more people using similar technologies. But they have a different name for this. They will call the bulk, which characterize 't Hooft anomaly as some kind of topological symmetries. A very different name, but only thing I can say is that it has a lot of applications in the recent year. I could not give a summarization of why this idea was useful, how it was. It's difficult to summarize them. But for example, I can say, okay, maybe I can say one thing. Why this idea will be useful is the following. Maybe this picture. So if you have some non-invertible domain wall in the bulk of ZA, if you have a non-invertible domain wall there, and you can see immediately, if you fuse this domain wall to the boundary, it will give a remember, what is the invertible domain wall? Invertible domain wall simply define the invertible map, right? So this invertible domain wall, if you fuse to the boundary, simply give a non-trivial duality on the boundary. In the recent year, it's become very popular to realize, okay, for example, the EM duality in the toric code will automatically, when you fuse to the boundary, become a so-called Kramer-Wiener duality for the Ising lattice model.
Excuse me.
Yes.
But there is one question from on-site participants. So could you continue discussion after the session? So
okay, sure.
Please ask question.
Sorry, just a very quick question. This is this is Chris Bourne from Nagoya. You very briefly talked about gapped and gapless domain walls, or gapped and gapless monoidal functors. Can you in 1 minute, maybe explain what it means for a domain wall to be gapped or gapless?
For domain wall is well, you're asking what's the definition of a domain wall be gapped or not gapped or gapless?
Yes.
I think this can be a gapped condition can be defined in the neighborhood. So you can talk for how to give a well, do you know like a level model or but like Tor code model, or it has a gapped boundary, but gapped boundary can be viewed as special case of domain wall, gapped domain wall. But so for example, if the topological order topological order by definition is gapped, if you consider a domain wall between two topological order, well, it can be gapped and gapless. So if the gap just means that in the neighborhood of the domain wall, you have a lattice model, right? This lattice model have a gap in the thermodynamic limit. Gapless then just in the thermodynamic limit is closed.
Yeah. So that's good enough for me. Thank you.
Okay.
Okay.
So since the time is up, let's thank the
Yeah.
speaker again. Thank you very much.
Thank you very much. Thank you very much.
Please wait a few minutes for preparation of the second speaker. Ah, 大丈夫かな？あれ？なんで？Yeah, sorry, the network, the condition of network is very bad this morning in Nagoya. So it takes us time. Excuse me, the third speaker is already online? No, not yet.
You mean the third speaker? I'm online.
Sorry?
Okay.
If it's possible, I'd like to exchange the order.
Okay, you
Since
mean
there's-
so I'll speak the next, right?
Okay.
Okay.
Are you? If you are ready, please share your screen.
Okay.
We are very sorry for it.
Okay, it's fine. Okay, could you see my screen share?
It takes time.
Okay.
Okay, we can see. Okay, so let's exchange the order of the speakers. So originally the third speaker, but the second speaker of this morning is Dr. Zhao. He will tell us central functor and condensation theory. So please start.
Okay, thanks for the introduction and thanks for inviting me to the workshop. Okay, my title today is Central Functor and Condensation Theory. Oh. Okay. In this talk, I introduced the notion of a relative center functor, which generalizes Cohn and Zhen's work on center functors. I'll develop the calculus of condensable algebras, by which I mean a pair of adjunction between codimension 2 and codimension 2 condensations and codimension 1 condensations. Okay. First, let me introduce to you some background. This talk relies heavily on the language of separable n categories developed by Cohn and Zhen. And I will first introduce some necessary notions and the terminology. Throughout this talk, we walk over the field C of complex numbers. A separable n category C is a linear n category such that C is Karoubi complete, condensation complete, which is developed by this notion is developed by Gaiotto and Johnson-Freer. And C is fully dualizable in a suitable Morita category. The collection of all separable n categories, linear functors, and higher morphisms form a separable n+1 category, in which we denote by n+1 vec. We use the convention that 0 vec is just the field of complex numbers, and 1 vec is vec, that is the category of finite dimensional vector spaces. There is a pair of adjunction, which we call sigma and omega, between the category of EM plus 1 algebras in n-vec and the category of EM algebras in n+1 vec, where the sigma sends EM plus 1 monoidal category to its condensation completion sigma C, while omega sends EM monoidal separable n category D to I'm sorry, this is hidden, and this should be the home category of the tensor unit of D. Okay. We have the sigma of n vec is equal to n+1 vec, and the loop of n+1 vec is n vec. In particular, there is a simple but astonishing formula which says n vec is the n-fold delooping of C, which says that everything can be obtained by iteratively condensing C, the field of complex numbers. A E1 monoidal separable n category is called a multifusion n category, and a E2 monoidal separable n category is called a braided multifusion n category. We see that the braided multifusion n category is braided fusion if its tensor unit is simple. Let AB be indecomposable multifusion n categories. We see that a separable AB by modulo M is closed if the canonical linear monoidal functor which gives the bimodular structure is invertible. We see that A is non-degenerate if the A bimodular A is closed. Okay. Let AB be braided fusion N categories. A multi-fusion AB bimodular is a multi-fusion N category X equipped with a linear braided monoid functor. Okay, like this. And we see that X is closed if psi X is invertible. And we see that A is non-degenerate if the multi-fusion A bimodular A is closed. And here we record that a multi-fusion N modular is equivalent to a separable algebra in sigma A. Okay, now I explain the relation between the language and the topological order. Okay, an n+1d here I mean space-time dimension. An n+1d anomaly-free topological order can be described in terms of the following equivalent ways. The first way is we can use a braided fusion n-1 category C to describe it. Here the objects correspond to codimension 2 defects of A. And we can also use a fusion N category, sigma C, to describe A. Here, the objects correspond to codimension 1 defects of A. Okay. Let us fix a non-degenerate multi-fusion N category C. Let Mn be separable left C modulus, and we use functor Cmn to denote the separable N category of C modular functors. And when M equals N, the functor category is multi-fusion. And we'll use left mod n+1 vec to denote the 1 category, where an object is an indecomposable separable left C modular, and a morphism is an equivalence class of C modular functors. We use this notation, maybe you can read it as fusion, closed fusion N, to denote the symmetric monoid 1 category. Where an object is a non-degenerate fusion N category A, and a morphism is an equivalence class of pairs Mx. Here M is a closed BA bimodular, and X is a non-zero object of M. Okay, here I introduced the relative E0 center functor. For left C modular M, the left C modular structure is equivalent to monoid functor. Okay, and the functor category is nothing but the E1 centralizer. And when M is separable, this functor category is non-degenerate. It is a non-degenerate multi-fusion category, and we can view functor Cm as the E0 center of M relative to C, and geometrically, the relationship between Cm and functor Cmm is demonstrated in the following diagram. Okay, you can view C as the original phase, and M is a domain warp, and the functor Cmm is the right hand side phase. We can also see that this phase is obtained from C by condensing M. Okay, M is a certain kind of condensable algebra. Okay, I introduce a theorem. Let C be a non-degenerate fusion N category, and then we may define a relative center functor from the category of indecomposable left C modulus to the category of closed fusion categories. Okay, this functor sends an indecomposable separable left C modular M to the non-degenerate fusion category functor Cmm, and sends the C modular functor F to the pair, to this pair. Here, F is an object in this category, right? Okay, to prove it suffices to check functoriality. Well, this is trivial, okay. Okay, then I'll introduce the relative E1 center functor. Let braided fusion, closed braided fusion N denote the symmetric monoid 1 category, where an object is a non-degenerate braided multi-fusion N category, and the morphism is an equivalence class of closed multi-fusion BA bimodulus. Okay, and let C be a non-degenerate braided monoid fusion N-1 category, so that sigma C is a non-degenerate fusion N category. Let multi-fusion C denote the 1 category whose objects in decomposable multifusion C modulus, and the morphism from M to N is an equivalence class of severable C central Mn by modulo L. Okay. Okay, now I introduce the first the important theorem, which says that the assignment which send M to this E2 centralizer, together with the assignment which send the bimodular the multifusion bimodular. Okay, it's not a multifusion bimodular; it's a C central bimodular. To this guy, this guy is defined as the loop of this guy. Okay, this together define a functor. Which we call the relative E1 center functor. Okay, from the category of multifusion C modulus to closed braided diffusion categories. Okay. The proof is almost trivial because our assignments coincide with the composition. Okay, this composition, and each of these arrow is a functor, so their composition is. Okay, now let me introduce the calculus of condensable algebras. First, recall that for braided diffusion N category C, a multifusion. Okay, sorry, there is a typo. A multifusion C modulo category. Okay, a multifusion C modulo category is the same as a separable algebra object in the fusion N+1 category sigma C. And we use this notation to denote the category of where an object is a separable algebra in the fusion N+1 category sigma C, and the morphism is an equivalence class of algebra homomorphisms. Okay, here we use algebra homomorphisms to be our morphisms, and given two objects in this category, our theory of relative center functor allows us to give a geometric construction of an algebra homomorphism from M to N in sigma C. And this construction is inspired by Kohn and Zhen's work. Okay, here is a large proposition, but I'll explain it later. Okay, let M and N be two separable algebras, then let F be an algebra homomorphism in sigma C. Then we have an equivalence of algebras in sigma C. Okay, it looks very complicated, right? Okay, which says the dimensional reduction. Okay, the tensor product of this guy and this guy is equivalent to N as algebra in sigma C, which send F box times X to FFX. Conversely, suppose we are given a multifusion modulo E and an equivalence phi looks like this of algebras in sigma C. And then this is the composition, okay, defines an algebra homomorphism from M to N. Okay, moreover, these constructions are inverse of each other. Okay, and then I'll give a geometric explanation of this theorem. Okay. According to the proposition, an algebra homomorphism F from M to N is equivalent to the following data. Okay, a multifusion by modulo L between these guys, such that L box times M is equivalent to N as multifusion C modulus. And physically, this means a gapped domain wall L such that the dimensional reduction of the triple is N. Okay, let's look at the picture. The original phase is C, and the M and N are two multifusion C modulus. Okay, and here we have shown that an algebra homomorphism from M to N is equivalent to such a domain wall, such that if I squeeze this face, so I glue M and L together, then I'll get this face. Okay, and that is this formula. Okay. Okay, now I introduce the calculus of condensable algebras. Let us return to the one categorical case. Fix a non-degenerate braided diffusion category C. Recall that a E2 condensable algebra in C is a connected commutative separable algebra. and we use condensable algebra E2C to denote the category of condensable algebras and algebra homomorphisms. And we use E1 condensable algebra sigma C to denote the category of condensable algebras and equivalence classes of algebra homomorphisms in sigma C. And we define a functor which is called R mod C, which sends an E2 algebra to an E1 algebra in sigma C, and it sends A to the category of right A modulos in C, and it sends an algebra homomorphism to this functor. Okay, and this functor here the left A modulo structure on B is induced by the algebra homomorphism F. Okay, and we'll define a functor in the reverse direction, and let Z be the following functor. Z send an E1 algebra in sigma C to this guy. Okay, this guy is the internal home of the tensor unit of M in C, and it is well known that the internal home is equipped with a canonical structure of condensable algebra in C, and this algebra has an interesting geometric construction. We do dimensional reduction to the bubble in C, as is depicted in the following picture. Okay. Here, recall that M is a domain wall of C. Okay, and we can form such a bubble, and if we do dimensional reduction to this bubble, we will obtain this guy, and it is a condensable algebra in C. Now I'll explain the action of Z on morphisms. Given the algebra homomorphism from M to N, recall that this can be given by a gapped domain wall L like this. Okay. And we define ZF to be the dimensional reduction of the following object in C. Okay. From this picture, we create such a bubble like this, and this L is this domain wall. What does this have to do with an algebra homomorphism from A to B? Okay. We use A to denote this algebra and B to denote this algebra. Okay. And we want to show that this guy will give a algebra homomorphism from A to B. Okay, let us observe this bubble. This object has the following properties. Okay, first, the dimensional reduction of this bubble is B. Okay, first you do dimensional reduction of the left square, and you see that it is just B. Okay, hence it acquires an algebra structure. And then this object is equipped with a canonical left A action, and this left A action is compatible with the algebra structure in an obvious sense. And then we could see that such a left A modular structure on B is equivalent to an algebra homomorphism F. Okay, and this completes our definition of the functor Z. So we have defined the action of Z on both on objects and on morphisms. Okay, and now I'll claim the main result without writing down more details. Let C be a non-degenerate braided fusion category. Then there is a pair of adjunction. Okay, between the category of E2 condensable algebras in C and the category of E1 condensable algebras in sigma C. Okay, this functor is R mod C, and this functor is Z, which we have just defined. Moreover, this functor R mod C is fully faithful, and the composition. Okay, you go this way and you go this way. This composition is equal to the identity okay, I'm sorry, here it should be identity of this category. Okay, it is a type. And using some mathematical terminology, we see that this category is a co-reflective localization of this category. Okay, and moreover, I believe this theorem can be generalized to higher dimensions. Okay, that's all. Thank you for listening. Is there any questions?
Thank you very much. So are there any questions, comments?
Okay, if there's no question, then I'll stop.
Excuse me. Yeah, I'm Shintaro Yanagida from Nagoya. So yeah, very interesting talk, and I think that your theory is very quite a natural one. But short question that is there any application or some explicit or interesting example of your theory?
Okay. So you mean some examples, okay, right? Oh, well, there are many examples, but I did not write them. For example, you can the Levin-Web models, I think, can offer many examples, and you can.
I agree that plenty many examples, but I'm asking some quite interesting example or some application to say mathematical physics or some quantum physics like that.
Well, I don't know what do you mean by applications, and I think if you take the Levin-Web models or quantum double model, and I think that can be interesting applications. Maybe I'm not sure what is the application you want to see. Okay.
So is there some example of this braided fusion category C that appear in some quantum physics or
okay,
physics?
You want me to take C to be some concrete fusion category, right? Okay, maybe so you can take C to be maybe I think the dream field center of rep G for some finite group G, and that is exactly theta Eve's quantum double model, or maybe you can add some maybe you can twist the model by a group cohomology, and that is also fine.
Then so you are showing your theorem. So this theorem, so in that example, so this theorem implies some physical consequence or something. Is there some application or some implication of your theorem to that situation?
So I have not tried yet, but at first on objects you can maybe given a domain wall of a arbitrary phase, and then you can create the condensable algebra corresponding to it using this functor. Okay, but this is an old result. Okay, using this functor Z, you can create a condensable algebra from each gapped domain wall of C. The key point of my theorem is to explain is to give the action of this functor on morphisms, on an algebra homomorphisms. But I have never seen detailed example in physics.
So it will happy if such a condensed algebra is, how to say, easy to treat more than the morphism itself. So then your theorem might make the problem more easy one or attackable one, I think. But anyway, so thank you very much for your comment.
Okay, thank you for your questions. So I'll stop sharing my screen. Okay.
And any other questions, comments, possibly from the online participants? So let's thank the speaker again. Thank you very much. Yako-san, are you ready?
Yes. Yes.
Okay, so the last speaker in the morning session is Yusuke Nishinaka from Nagoya. He will tell us a review of vertex algebra and chiral algebras. So please start.
Thank you for introduction. First, I'm so sorry for the trouble. I couldn't enter the Zoom. And thank you for changing the order of talking. Today, I'm going to talk about vertex algebras and chiral algebras. Vertex algebras were introduced by Borchers and so please wait.もう一回。はい。ただ、なんか、共有が停止されました。もう一回停止しなので、共有します。
Please wait.
Sorry.
Okay,
Uh,
let's proceed.
Vertex algebras were introduced by Borchers, and they are known as algebraic framework of two-dimensional conformal field theory. On the other hand, there is a geometric framework of CFT, which is called a chiral algebra. This notion was introduced by Borchers, introduced by Beilinson and Dornfeld using the theory of D modules and that of operands. In this talk, I would like to explain these two things. The first is for smooth curve X and quasi-conformal vertex algebra B. We can attach this data to chiral algebra on X. The second is the theory of operat, in particular the chiral operat and its algebraic counterpart. So first, let me talk about vertex algebras. Vertex algebra consists of C-linear space called space of state and linear operator T called translation operator and an element called vacuum and linear map Y from B to the space of formal series. And this linear map Y is called the state field correspondence. And for an element A of B, we expand this formal series in this form. And this is called the vertex operator of A. The axiom of vertex algebra implies operator product expansion of the vertex operators, and OPE is a fundamental technique for calculating the interaction of two fields. For element A and B, the OPE of these vertex operators are given like this. In physics literature, this is written in this form. And this OPE is equivalent to the commutation relation of the coefficient of vertex operator for all m, all integer m and n. Here is an example of vertex algebra called the affine vertex algebra, or the West-Zumino-Witten model in physics. Let J be a finite dimensional simple Lie algebra, and J hat be the affine Lie algebra. The Lie bracket is defined here. For a complex number K, it's called the level. We define VKJ as the induced representation. Here, ket K is a one-dimensional representation of this sub-Lie algebra defined by these relations. Then VKJ has a unique structure of vertex algebra such that ket K is the vacuum, and the state field correspondence is defined by this formula. Affine vertex algebra is not just vertex algebra, it is a conformal vertex algebra. Conformal vertex algebra is a vertex algebra which has internal symmetry of the Virasoro algebra. Conformal vertex algebra consists of vertex algebra V and an element omega called the Virasoro vector, and a complex number C called the central charge. And a part of actions is here. If we expand the vertex operator of omega in this form, then the operator Ln should satisfy the fundamental relation of Virasoro algebra. Affine vertex algebra is a conformal vertex algebra. If the level K is not equal to minus H check, here H check is the real Coxeter number of J, and then VKJ is a conformal vertex algebra of this central charge. And its Virasoro vector is defined here using a basis of J and the real base with respect to the normalized invariant form. Next, I will explain the geometric description of vertex algebras. We fix X and vertex algebra. Actually, the story is true for quasi-conformal vertex algebra, which is more weakly concept than conformal vertex algebra. In this setting, we can construct the bundle Bx, whose fiber is isomorphic to B. This bundle Bx is called the vertex algebra bundle. And for more details, I refer to the book by Frenkel and Bensby. For and Bx in calligraphy is a sieve of sections of the bundle Bx. And I want to give a D-module structure on Bx. So for this purpose, we need the following local description. For a point X and a local coordinate uz of X, the restriction of Bx to U is isomorphic to the tensor product of B and OXU. The OX module Bx has a flat connection defined as follows. For a point X, take a local coordinate UZ, and define a morphism of sieves using this local description and the Virasoro operator of B. Then this canonically defines a connection nabla on Bx. And Bx has a structure of left dx module by this connection nabla. Let Bxr be the corresponding right dx module. That is, Bxr is the tensor product of Bx and the canonical sheaf omega x. Bxr is not just a D module, it has operation mu induced by the vertex operator of V. And this operation mu satisfies the skew symmetry and the Jacobi identity. Generalizing the structure of Bxr, we arrive at the notion of chiral algebras. Chiral algebra consists of right D module A and morphism mu called the chiral operation, satisfying the skew symmetry and the Jacobi identity. And to state the skew symmetry, we need to switch the input of the chiral operation. And to state the Jacobi identity, we have to compose the chiral operation. But this is more complicated than in the case of ordinary algebras because A is a sheaf. To describe the switching the input and the composition of the chiral operation, Beilinson and Drinfeld introduced the chiral operand PCH. I want to go into the precise definition of the chiral operand, but I explain the operads in general. An operand is a device that describes the composition of operations. To introduce operads, consider n operations on a fixed linear space B. We observe the following three things. First, of course, operations can be composited. For operations Fk and G, we have the new operation by the composition of linear maps. And second, there is a unit operation that is identity map on B. And third, the input of the operations can be swapped. For example, if F is a binary operation, then we can switch the input of F and we get the new operation. In general, for n operation F and a permutation sigma, we get the new operation F sigma. The notion of operads is a generalization of the above observation. Operad consists of a sequence P, where Pn is a right Sn module for each n. P is called the S module. And a linear map gamma for each n and M1 to Mn. This is called the composition map. And an element of P1 called the unit. The first example of operads is endomorphism operad. As the S module, this is the space of linear maps with light action of symmetric group defined here. And composition map is defined by the composition of linear maps. And the unit is the identity map. Then these data forms an operand. And algebraic operations have special symmetries. For example, the Lie bracket satisfies the skew symmetry and the Jacobi identity. To describe these special symmetry, we use the morphism of operands. For example, there are operands called commutative operand and the associative operand and the Lie operand. These operands are defined to satisfy these bisections. For example, morphism from Lie operand to the end morphism operand corresponds bijectively a structure of Lie algebra on B. In this way, we can formulate algebraic structures in terms of operands. Back to chiral algebras. Beilinson and Drinfeld define the structure of chiral algebra on a light dx module A as a morphism from Lie operand to the chiral operand. So it is natural to ask what is the algebraic version of the chiral operand. In other words, what is the operand of vertex algebras? Bakarov, Dizor, Helani, and Katz introduced an operand, which is a purely algebraic translation of the chiral operand. And they proved that morphism from the Lie operand to the operand corresponds bijectively the structure of vertex algebra on B. So the operand encodes the structure of vertex algebras. So let me conclude with some remarks. First, conformal field theory with supersymmetry have also been actively studied in physics. And Helani and Katz introduced the notion of supersymmetric vertex algebras or Suji vertex algebras. Helani and Katz introduced the notion of Suji vertex algebra to formulate the calculation of superfields which appeared in SFT. And my supervisor Yanagida and I constructed an operand which encodes the structure of Suji vertex algebras. That's all. Thank you for your attention.
Okay, thank you very much for a nice review and your introduction of your recent results. Are there any questions, comments? From on-site participants, please. Say you are learning.
Okay. I'm a student of Nagoya University. I'm Iwane Takumi, and I ask you question. The global section of VGR is has an interesting structure.
BXR.
Yes. Or chiral algebra. I think the global section of chiral algebra or VXR, sorry, is interesting.
Yes.
Uh, yeah, I wonder the structure. I wonder its structure. So it is known.
Well, VXR is D module with operation called chiral operation, and this is example of chiral algebra.
Yeah, it's global section.
You mean sorry, I'm not sure.
Don't you have an immediate answer to that question? Okay, so
Sorry.
please discuss after the session.
Yes.
Other questions, comments? Yep. One more question from.
Thank you for the interesting talk. So,
please, yeah.
I'm Hayato Arai from Nagoya University. So I cannot catch up with all the content of your talk. So please go to the summary slide.
Last
slide, yes.
Sorry, please wait. Yeah.
So you mentioned that by considering the operate structure, so the operate structure is benefit to the calculate the supersymmetric vertex algebra.
I mentioned that operates fit to formulate the algebraic structures, not supersymmetry.
You mentioned the operate is helpful for the formulation
of algebraic structures.
Then, so can you give a more concrete benefit for the formulation?
For example, there are general theory of operatic cohomology. It's for the operates called quadratic, we can develop the cohomology theory in general. So once we formulate algebra in terms of operates, we get cohomology of these algebra by theory.
Okay, so
Can I ask a question?
Yes.
You formulate the operatic formulation of this supersymmetric vertex algebra. I wonder what is the relation between the supersymmetric conformal vertex algebra? Because in that case, you need a lot of super symmetry generalization of vertex algebra, would in general give you a super conformal algebra. So I was wondering, can you also generalize your formulation to that context? To the super conformal.
Sorry.
Excuse me. So could you say your question again? So there's some trouble on our side. I'm sorry.
I see. Okay. Let me say it again. Okay. You have an operatic formulation of the supersymmetric vertex algebra. Do you have a super conformal? The operatic formulation of super conformal, like usually some people call it vertex operator algebra. That means you have to have super conformal algebra, which is a generalized universal algebra. So sometimes in physics or in some mathematic people, they will use a super Riemann surface to give operative formulation of that. The reason that I asked this is that the supersymmetric vertex algebra, it appeared in the superconformal field theory, in which automatically include the superconformal algebra. So I was wondering, so my understanding is that the super vertex algebra is not it's not a complete did not catch the complete or maybe I could be wrong, the Versaro part, the superconformal generalization of Versaro. That will usually be the so-called say equal to superconformal algebra. So I was wondering if you have in your operator operator formulation, do you have can you catch that part? Can you catch the superconformal algebra part?
I think you you mentioned the superconformal algebra.
Yeah.
It is also called vertex Lie algebra or conformal Lie algebra. Is it right?
No, I'm not sure. No, I don't think so. Because the Versaro algebra have a super symmetric generalization. Sometimes maybe, for example, it can be n equal to superconformal algebras. So in your case, how many supersymmetry do you assume when you say super symmetric?
Oh, yeah, I see. Okay, I think
I think
supersymmetric vertex algebra introduced by them is
my impression there is an equal one at most. That's my I left the field for a while, but if I remember correctly, in using physics terminology, there will be an equal one. The reason I asked this question is because if yeah.
Excuse me.
Oh, is it lost again?
Last line of this slide. Yeah, we are seeing ahead. Nishinaka-san's slide, and in the last line, actually, our work includes n supersymmetric vertex algebra. So what you are saying, the super CFT is also included in your work.
Oh, you mean also include? So if it is included, can you generalize to non-chiral theory if it is included?
Working, but it is possible. As far as I believe. Yes.
Well, the reason I ask is that if you can generalize to non-chiral, then you can study deep brain. Then you can study BPS brain using this, which break half of the supersymmetry. That would be really interesting. But nobody know how to do that. As far as I know, 10 years ago, nobody know how to do that. So I don't know.
It is still a very big problem.
Okay.
How to leverage in this context. Yes. Thank you very much for the comment.
Okay.
Thank you.
Okay.
Oh, any other questions? Comments? So if not, let's thank the speaker again. Thank you very much.
Thank you.
Thank you. So this is the end of the morning session. Thank you very much for joining us. So the afternoon session starts at 2:30 in Japan time and 1:30 maybe in China. Okay.